7.1 Dynamic equilibrium in chemical system. When we talk about equilibrium, consider this reaction. CO2 gas will convert to CO2 aqueous. So this, when you have a two-way reaction, see forward and backward, it means both of this forward and backward reaction happening at the same time, and equilibrium can reach. So knowing that dynamic equilibrium is the balance between forward and the reverse process occurring in the same rate. Means in the same rate as CO2 turns to CO2 aqueous, the same rate CO2 turns to the CO2 gas. Forward reaction is equilibrium from left to right. So from left to right is forward, and reverse is from right to left. As you see, this is two arrows. So here's the solubility equilibrium. If you look at this picture, at the beginning, you have some solid that turn into the aqueous. As it goes, the solid turn to the aqueous, and it starts that the aqueous turn into the solid. And as the time goes, the rate that solid turn to aqueous will be the same as the rate aqueous turn to the solid. At this picture, the equilibrium is reached. The same amount it turned to the solid is the same as the same amount it turned into aqueous. Here is solid, it turned into Ca2 plus, and so for aqueous, this is two-way reaction. Okay. So here, when you have solid turn to the aqueous, this is the solubility equilibrium. Now, phase equilibrium. When you have between two different phases, liquid turn to the gas and gas turn to the liquid. This is a phase change. Now, chemical reaction equilibrium. Look at this. N2O4 turn to 2NO2. At the beginning, we just have N2O4, so we have some concentration. Then the concentration decreases. As it decreases, it means some of that is turning to NO2. Means if you have NO2, the concentration at the beginning is 0 and it is increasing. But after some time, the concentration of both remain constant, right? After this point, after this time. At this time, the equilibrium is reached. Okay, so here is percentage reaction is the actual product yield divided by theoretical yield. So it means when you do the experiment, it's not perfect. Also, the actually that you're doing with the experimental is going to be much more less than theoretical. Theoretical is when you're calculating mathematically. So actual divided by theoretical multiplied by 100 is going to give you the percentage of the reaction. Okay. So if the percentage of the reaction is much less than 1%, means the reaction doesn't happening, is no observable result. If the percentage of reaction is more than 99%, so it means it is complete quantitative. So it's going to be just forward reaction. So if this is kind of more than close to 99, means it's just a one way. It's just more product. You have very product is much more than the theoretical. Is one way. Reaction that achieve somewhere between the kind of more than 50%, because both ways, less than 50% is favored. Less than 50%, it is favored your reactant. greater than 50%, it is favor your product. Consider the following equation for the formation of the hydrogen fluoride. H2 plus F2 give you 2H. This is a two-way reaction. If the reaction begin with 1 mole per liter concentration of H2 and F2, so we have concentration of F2 and H2 1, both of that is 1 mole per liter. Calculate concentration of H2 and HF at equilibrium if the equilibrium concentration of the F2 is given 0.24. So for this kind of question, you need to establish ICE table. So ICE, the first column is initial, you put initial concentration. The second column is change. And the last column is equilibrium. We call it ICE or ICE table. So from the top, you just put your reaction, H2 plus F2 give you 2HF. Initially, we have 1 mole per liter of H2 and 1 mole per liter of F2, and we have nothing for HF, we put 0. For second column, we put the change. Here, if this is forward reaction, because we just have a reactant, the concentration will decrease by some amount of X. That's why I put negative X. Here, the same thing, negative X. And we increase the concentration of HF is increased, but because the coefficient is 2, is going to be increased by 2x. Put that to be positive. For equilibrium, it's going to be just initial added to the change. 1 minus x, and here is 1 minus x, and here is 0 plus 2x, which is 2x. Since the concentration of the F2 or H2 is given, as you see, look at that at equilibrium, concentration of the F2 is given 0.24. Means F2 here is 0.24. We just rearrange it for X. Once we have X, so you can find the concentration of H2 at equilibrium, concentration of HF at equilibrium. So here is, bring the X to the other side, become positive, bring 0.24 here. It becomes 1 minus 0.24 is going to be 0.76. So 1 minus 0.76, again, the equilibrium of that going to be 0.24. 2, and here going to be 2 multiplied by 0.76. 1.52. So we got concentration of HF at equilibrium. We got concentration of H2 at equilibrium. Is another question. When the ammonia is heated, it decomposes into nitrogen gas and hydrogen gas according to the following equation. With 4 mole of the NH3 is introduced into 2-liter rigid containers. From that, we can find concentration. Concentration is going to be mole per liter. So 4 divided by 2. Going to be initial concentration of the NH3. And the amount of the ammonia changes as shown. So this is the changes happening in this figure. Determine the equilibrium concentration of the other 2 entities. As you see, it is stored at 4 mole. And sometimes it becomes constant. The constant, it will be 2, right? 2 mole. Again, we have concentration at the beginning is 4 divided by 2. Concentration at equilibrium, it is 2 divided by 2, so it's 1. So we have initial concentration, 2 mole per liter. And here is final concentration. Equilibrium concentration is 1 mole per liter. Now we need to establish the ICE table. So let's do that ICE table. Here is ICE table. So just write down the reaction. So ICE. Initially, this is 2 mole per liter. We have nothing at the beginning for the product. So since the coefficient is 2, so change is going to be negative 2x. Here the coefficient is 1. It's going to be positive 1x. Here's 3, it's going to be positive 3x. So for that would be the equilibrium would be 2 minus 2x, 0 plus x, 0 plus 3x. We know the concentric equilibrium of that is 1. So, right, we calculated it. But 2 minus 2x is 1. We solve for x. X is going to be 0.5. If you know x, so it's going to be 0.5 here. And for this one, going to be 3 multiplied by 0.5, which is 1.5. See, we have x 0.5, and for the 3x is 1.5. Here is another question. In a gaseous reaction system, 0.2 mole of hydrogen gas is added to 0.2 mole of the iodine. So in a 2-liter container. So we have volume, we have mole. So initially we can find the concentration initial. So 0.2 divided by 2, going to be 0.1 initial concentration of H2. 0.2 divided by 2, again, going to be 0.1 initial concentration of I2. So determine equilibrium concentration of H2 and HI. And it's the equilibrium system contains 0.04 mole of hydrogen gas. Again, divided by 2 to find a concentration at the equilibrium. We establish ice table, write down the reaction, ice initial change equilibrium. So initially you had 0.1 mole per liter H2, 0.1 mole per liter of I2. You didn't have nothing of the product. The change is going to be, because the coefficient is here is 1 and 1 here, so it's going to be negative x, negative x. Coefficient is 2 is going to be plus 2x. So 1 minus x here, and here 1 minus x here, and here is plus 2x. Since here is 1 minus x, right, for equilibrium here we'll have 1, which is given to be 0.2, right? We have that. So we solve for x, so x is going to be 0.8. Again, you put x here to be 0.8. 1 minus 0.8 is 0.2 is equilibrium concentration of I2, and here is 2 multiplied by 0.2, which is 0.4 is the concentration of the HI, just mole per liter, all of this. So for the practice, please do question number 6 and 7, page 437. Also question number 4, here, page 437.